In this video, we'll look at Sudoku as an NP-complete problem. First, we'll look at Sudoku itself. Sudoku is a partially filled n by n grid which must be filled with numbers 1 through n. Now, n must be such a number that under root n is a positive integer because the grid contains subgrids of size under root n by under root n. Now, the rules are simple. No row, column, or subgrid can have a number repeated. So let's define this problem now as a decision problem. Now, given a partially filled n by n grid, does a valid solution exist? Now we'll have a brief look at what it means to be NP-complete. The hardest problems in NP that if solved, then all problems in NP would be solved. This is the NP-complete class. Now, for this, a problem must meet two conditions. First, it must be an NP, and second, it must be NP hard. Now, how do we know if a problem is in NP? There needs to exist a polynomial time verifier for it. So in this case, P can take M, which takes an input G, which is our grid, and S as the certificate. So S would be the assignments, which would have a length of less than n square. Now for each assignment, we know that there is 3n work required, because if there is an assignment, then the subgrid needs to be checked, which contains n numbers, the row which contains n numbers, and the columns. This amounts to 3n. Since there are almost n square assignments, the total work amounts to almost 3n cube, which is an O of n cube. So we have shown that a verifier exists in polynomial time. Now for this problem to be NP hard, we need to show that all problems in NP can be reduced to it. So instead of showing that all problems in NP can reduce to Sudoku, we can choose one NP complete problem and reduce it to Sudoku. Then essentially we'd have shown that all problems in NP can be reduced to Sudoku. Now this was the fairly straightforward part. Now we'll move to a more complex part, which is an actual reduction of an NP-complete problem to Sudoku.
To show that Sudoku is NP hard, we reduce the 3-sat to Sudoku. The reduction involved transforming any instance of 3-sat into an instance of Sudoku such that the 3-sat formula is satisfiable if and only if the corresponding Sudoku puzzle has a valid solution. The 3-sat problem can be summarized as follows. The 3-sat consists of an input, a Boolean formula phi, in 3CNF form, consisting of a conjunction of clauses, where each clause is a disjunction of exactly 3 literals. The goal here is to determine whether there exists a truth assignment to the variables that makes the formula true. For our reduction, we will construct a Sudoku puzzle from any given 3-sat formula such that if the 3-sat formula has a satisfying assignment, the Sudoku can be completed, and if the Sudoku puzzle can be completed, the corresponding truth assignment will satisfy the 3-sat formula. We will now perform a step-by-step reduction. Step 1. Input 3-sat formula. Let phi be a 3CNF formula with variables x1, x2, and so on until xn, and clauses c1, c2, and so on until cm, where each clause contains exactly 3 literals, either a variable or its negation. Step 2. Constructing the Sudoku grid. We will build a Sudoku grid whose structure encodes the variables and clauses of the 3-sat formula. To keep things simple, assume we work with a standard 9x9 grid. However, for larger or more complex 3-sat instances, we can generalize the grid size, example n squared times n squared for larger formulas. Step 3. Encoding variables. Each variable xi in the 3-sat formula is represented in the Sudoku grid by a pair of possible values in certain cells, corresponding to whether the variable is true or false. We will assign a pair of cells for each variable in a way that ensures only one of the two possible values can be chosen. This will simulate a truth assignment for that variable. For example, for each variable xi, we can use two cells in a row or column assigning one cell to represent xi equals to true and the other to represent xi equals to false. The structure of Sudoku ensures that only one of these values can be filled. Step 4. Encoding clauses. Each clause will be represented by a subgrid or region in the Sudoku puzzle. For each clause, we will ensure that at least one literal must be true by constructing the puzzle so that one of the cells corresponding to the literals in the clause must be filled in such a way that the clause is satisfied. For example, if a clause contains the literals x1 or not x2 or x3, we will place constraints on the corresponding variable cells such that at least one of these literals must be set to true. We can do this by choosing 3 cells in the grid for the clause. For example, let's use cells C1, C2, and C3 for this clause, and by linking this clause cells to the literals. We will ensure that each of these clause cells is connected to the truth values of the literals x1, not x2, and x3 in the following way. If x1 is true, then the first cell C1 can be filled. If x2 is false, that is, not x2 is true, then the second cell C2 can be filled. And if x3 is true, then the third cell C3 can be filled. This linking can be done by ensuring that the available numbers or candidates for the cells C1, C2, and C3 depend on the truth assignments of x1, x2, and x3. Step 5. Enforcing Sudoku constraints. The rules of Sudoku ensuring that numbers appear exactly once per row, column, and subgrid will naturally enforce the logical structure of the 3-sat formula. By carefully placing the variables and clauses within the grid, we can ensure that any valid Sudoku solution corresponds to a satisfying assignment for the 3-sat formula. It is worth noting that some cells of the Sudoku grid will be pre-filled with numbers to enforce constraints corresponding to the structure of the 3-sat formula. These pre-filled cells help ensure that only valid truth assignments which satisfy all clauses lead to a completed Sudoku grid. Correctness of the reduction. From the reduction, we can see that if there exists a truth assignment that satisfies the 3-sat formula, we can use this assignment to fill in the corresponding variable cells in the Sudoku grid. This assignment will ensure that all the clause-related subgrids are filled correctly and the Sudoku puzzle can be completed according to the rules. Conversely, if the Sudoku puzzle can be completed, the corresponding values in the variable cells represent a valid truth assignment for the three-side formula. The structure of the puzzle ensures at least one literal in each clause is true, meaning that the formula is satisfiable. Therefore, the three-side formula is satisfiable if and only if the corresponding Sudoku puzzle has a valid solution. What we have just shown now is that Sudoku is NP complete. We have shown Sudoku is NP by building a polynomial time verifier, and we have shown that Sudoku is NP hard through polytime reduction from the three-side.